I think we're ready to get going. Welcome back, everyone. So we're really close to done with chapter 2. In fact, in a real certain sense, once we got through section 2.7, that was the main meat of that chapter. 2.8 is going to be kind of rehashing, giving some formal definitions of what are the symbols for a derivative and those kinds of things. And really, we're just going to focus on, if we take a derivative, that is itself a brand new function. So we could graph that function and we could differentiate it again if we'd like. So that's the major things we're going to be taking a look at today in section 2.8. Well, any questions, folks, before we get started? Okay, it's kind of a short week because we had a nice Labor Day vacation. So that means assignment 3 is only going to involve these two sections here. So from 2.8 and 3.1. We also have our upcoming exam. Our exam is only going to go up to these sections right here. Although it involves 2.8, I'm really going to only use a 2.8 problem that looks more like the 2.7. So nothing too wild, since there's a short turnaround from this week all the way to our first exam next Monday. So our first exam will be in this class. I write it as I'm targeting it as more of a 60-minute exam. So our class is 67 minutes. Last 7 minutes are more for just checking your work and that kind of thing. On the exam, these are the scientific calculators that are allowed on the exam. Honestly, I try to make exams that we really aren't going to calculate a whole lot on. So the scientific calculator is more just as a safety and a comfort if you want to double check a couple numbers. Also, you're allowed to have a single page of notes of size 8.5 by 11 inches, front and back with anything you like on it. So it could be handwritten, machine printed. I think formulas are a good idea, or anything that's going to help you get through these kinds of problems. And last thing I put here that's new is the sample exam 1 problems. What this really is an attempt to write out what a test bank might look like for this course. So it's going to go on a section by section basis and show what problems would be considered good exam 1 problems for this class. In fact, when I go to write my exam 1 questions, I always check something for those questions. A good exam 1 question is similar to something on this document, similar to something on your assignment that you did, and similar to something that's in the actual lecture notes itself. So something that we've hit essentially 3 different ways would make it a great question. If it's something we only saw on the homework, we saw maybe on assignment 3 or 2, it might be on the exam, but it may not be a preferred question. Well, any questions, folks, so far? Okay, I'll talk a little bit more about the exam when we get to our Thursday's class. That's already tomorrow. But if you want to get studying early, here are what the questions look like. If you scroll all the way down to the very bottom, there's some solutions down below as well. It is a long document, so if you decide to print it out, I'd use the ISU printers since you've already paid for a printing account. They'll save you some money. And so our goal for today is practice more about section 2.7 with the rehash topics in 2.8. Well, any last questions, folks, about the announcements? Okay, let's get started then. And I think I am forgetting one thing. I have some homework to pass back, but how about we do that after class is over? That sounds all right to folks? Awesome. So to start off class today, there was a question from the class about problem number 13 in the homework. This one, I believe I heard it was section 2.7, right? Gotcha. Yes. So from section 2.7, they ask us to consider this displacement function right here. S is 1 over t squared. Right away, you could say, if you like, that this is a new function f of t. That's valuable because the formulas that we use function notation. They might not use just a s or a y function. Yeah, but we didn't get too far on there. Yeah. Awesome. Glad to hear that. So the portion I'm going to take a look at is really this portion right here. And I'll leave the rest of the class to get through the rest of those. The first thing that they're asking for when they say find the velocity at these various times is we're really just going to write v of a. That's going to stand as our velocity function. And then this is the part that you were mentioning as well. Probably, yeah. The formula we're going to use goes f of t. Oh, before that, we're taking the limit as a new variable h goes to 0 of the function f of t plus h minus f of t divided by h. And the core question about this one is really just kind of the mechanics of getting through dealing with the fractions and finally canceling so we can calculate the limit. So I'll leave it up to that step as we go through this. First thing we want to do next is, here's our f of t function. But we need to put in f of t plus h. Some people just put it in all in one line, make one huge limit, or you can use the method of just divide and conquer, write out f of t plus h first. Really always up to you. I'll go with this strategy of writing it out this way. F of t plus h means we go to this function, which becomes 1 over t plus h to the power of 2. So that's our first part. Then this f of t here is really just copying. Does that make sense to folks to this stage so far? Okay, now when we go to the next step, this becomes the limit as h goes to 0. And whenever I detect there's probably going to be fractions in this process, I take this h here, and I'm just going to factor it to the left as 1 over h multiplying something else. Next, f of t plus h, we'll throw in this quantity, 1 over t plus h to the power 2. Highlighting these in yellow just to show where those things are going. Then minus, here it says f of t, and I'll just throw in 1 over t squared. So that's how this starts off. Then it's the wonderful world of dealing with fractions. The process of getting through these is usually not too bad, but it just takes practice to become comfortable with it. Any questions at all, folks, to that stage? Awesome. Then on the next step, I'm just going to write out limit h goes to 0 of 1 over h multiplying. I'm going to expand out these fractions because now what we're going for is least common denominator. And this is the strategy that, it always looks a little bit weird to me, but it absolutely works. There's no violation in algebra. Go to the denominators and just look at what factor is missing. On this denominator, we have a t plus h squared, meaning we're missing t squared. So back here, just throw it in, t squared, and throw it into the numerator so that this equality here is still maintained. Then back over to this one, we put in what's missing, which is this time t plus h squared. Oh, that's an eraser. Let me try again. T plus h squared above and below. This is where the limit starts to look not so bad. It's going to clean up from here on out. It'll become the limit as h goes to 0. I need a parentheses here because I have two different fractions, but we're now combining them to 1. So we can drop the parentheses at this stage and write 1 over h is multiplying one overall fraction with t plus h squared times t squared down below. And above, we'll take the subtraction of the numerators, t squared minus t plus h squared. So that's how this one ought to go. There's still some work to do here in cleaning it up algebraically, but you have to expand the t plus h quantity squared to get the 3 different terms. Distribute your negative sign into it, and you'll get all the cancellations that you're expecting. They'll finally allow h down below to cancel into the numerator, and so you can use direct substitution. Does that make sense to folks to that step so far? Yeah, go ahead. Actually, for the bottom, it's usually best to leave that one alone. I would leave it just completely undistributed in that format. There's no harm if you did expand it, but the reason I leave it alone is the only reason to distribute the numerator is because we're trying to cancel this h with this h. So that's purely the main reason to distribute up above. If we distribute everything below, it becomes a little bit longer, but there's no cancellation, so no real benefit for the denominator. Other questions with this one so far? Okay, I'll leave the rest of the algebraic matters here going off to the left, the dots for you folks to sort out. But if you do have further questions on getting through the algebra, I'll be happy to help out. Well, that was our question to start off class today. And thanks for that question. I'm always happy and willing to begin with a question to start us off. If we take 10 minutes to do that, I would say that's 10 minutes well taken. Other questions at the moment, folks, before we go to our next topic? Okay, so anytime there's a question for class that just feels like it deserves to be in the notes, you'll still see the title at the start of the notes. But if you see a problem in a section number, just assume that was an earlier discussion. Then section 2.8 starts officially right down here. What I've done is I've just duplicated a definition from section 2.7. So that's the nice part. It's really kind of a rehash. It says the derivative of function f. We'll denote it by this f prime symbol that you see right here. And it's just that specific limit, the limit of the difference quotient as h goes to 0, provided that limit actually exists. Part of what we'll do today is look at conditions that ensure it must exist. And this part right here is really the geometry of the whole situation. Let's highlight this in yellow, because this is one thing about the derivative that is definitely worth always keeping in your mind. The derivative is saying something geometrically about the original function. If I take the derivative at a point x f of x, it'll be equal to the slope at the tangent line right at that point. That's what the derivative gives you, slopes essentially. And if that's the case, you could take a graph of a function, y equals f of x, like you see here on problem 4 out of our book, and use that graph to sketch the derivative, y equals f prime at x. This is a hard problem. I have to be right up front and honest about it. It's hard maybe because I'm just not very artistic. There's a lot going on. So it's not something I would ask directly on exam, but it could be a valid homework problem. So let's give this a try and do it carefully. The whole idea to that problem is what you see highlighted in yellow. So before I go to give the sketch, I want to start by looking at some slopes that are easy to find on this graph. If I go here, I can't tell you much about that slope. I don't know what the value is numerically, but I know the sign. Would you say the slope here of the tangent line, is it positive or negative? Absolutely. Notice the curve is decreasing. That means the slope has to be negative. Until you get here, that point turns out to be extremely special if you're dealing with derivatives. Even if you're not graphing it, that point is still special. Those points are what are going to lead us to optimization in chapter 4. If I go right here, I want to change the colors, let's go to green. Then I can tell you the slope right at that location. Anyone happen to know the slope of the tangent line there? It's 0, absolutely. It's a horizontal tangent line, so it must have slope 0. That means we do have a point right from here. Likewise, this point would be called a local maximum because nearby it's the highest point. It also has slope 0. So look for where there's local maximums, local minimums. You know the derivative value there, it's 0. Because the derivative is the slope of the tangent line, and that horizontal tangent line sketch is at slope 0. So last one, slope equals 0 there. That at least gets us started. So what I'm going to do next is sketch a graph. Actually, I think I want a little bit more space, so it's not too crammed. I want to sketch a graph that goes like this. I'm trying to duplicate the exact scale of what you see on the top graph. The top graph is y equals f of x, the original function. And here we're going to attempt a plot of y equals f prime at x. Again, just a reminder on that prime symbol, try to give it a good angle. If it looks like a 1, I mean, I'll assume you mean the derivative, but it would really have a different meaning in that case. So here's f prime at x. We have 3 different values. The derivative is 0 here, here, and here. And so just go directly down. There's 1 point on the graph. Here's another point on the graph here. And here's the last point. I'm putting these directly under the points we indicated up above. They go right on the x-axis because that's where the derivative was 0. Next, we need to look at a little bit more analysis to get everything else, right? I have 3 points, but we need infinitely many. So let's back up here to this original graph. I'm going to break it up into regions that look like this. My graph is now broken into, let's see, 1, 2, 3, 4 different regions according to where the derivative was 0. Now on this far left region, we said f is decreasing. All right, DEC for decreasing. Let's define it here. And that means the slope of all the tangent lines is always negative. That's what we were saying earlier. If we imagine a tangent line here, function is decreasing, slope of the tangent line is also negative all at the same time. But if the slope of the tangent line is negative, that means the curve is below the x-axis because the derivative is that slope. So in this region, it starts below the x-axis. Let me get the right color though. Here's where the derivative went to 0. And now let's look above. And the region from here to here, the function's increasing. That means the slopes would be positive. Let's put a little bracket. F, I, and C is what I'll say. Now let's define it. I and C means increasing. And increasing increasing function means the tangent lines, even though I can't say their precise values, would you agree they're all going to be positive? Awesome. Until you get to right here, right? That's where it goes to 0. So where the derivative is 0 are the massively important cut points where the curve itself is jumping above and below the axis. So here I'll write m bigger than 0. Down below, m is the slope. If it's bigger than 0, it looks like this. It's going up. It has to go back down to hit this point that was defined. But now you probably see the rest of the pattern, right? It's decreasing down here. So my curve has to be below the x-axis. It has to go up and hit that point again. But it's increasing up here. And so the curve must shoot up like that. So even though my sketch of the derivative is not guaranteed to be perfect, qualitatively, it would be the right kind of shape. Let's finish out the rest on this. Here we say f is decreasing, which means the slope is negative. And here, f is increasing, which means the slope had to be positive in that location. The slopes being positive or negative is the whole thing that controlled where the curve was, above or below the x-axis. So we did it, folks. That's our first sketch of an honest derivative. Tricky work, best left for actual practice, like say on a homework. I probably wouldn't ask this as an exam question. But any questions at all with this one? Okay, again, it makes me kind of uncomfortable. I'm not great at freehand sketching curves like this, but when I go to grade yours, I'll keep that in mind. It could be a little bit crazy, more wonky than this. As long as your curve is in the right location, above or below x-axis, your 0 points look about where they should be, where the horizontal tangent lines are 0, you would always get full credit on those kinds of sketches. Well, that's what the derivative looks like. It's definitely a function. So if you wanted to, you could do this again and say, what's the graph or the next derivative of this function right here? That's like a long game of telephone, so we'll never do that. But the important thing to remind yourself is, if that's an ordinary function and it's differentiable, meaning that limit exists at all values x in its domain, then f prime is just a whole new function coming from the original one. Well, let's take a look at our next concepts. We have an idea of what the derivative of a function would look like based on the original function. But here's a couple of interesting theorems that could tell you, just at a glance of a graph, where a function is not differentiable. Theorem 4 is the theorem that was stated right out of the book. It says, if f is differentiable at A, then f is continuous right at A. So it turns into really an if-then statement. The hypothesis is differentiability. And it tells us, if you know you have differentiability, we have continuity guaranteed. I would say the real meat of this theorem is that differentiability is stronger than continuity in that particular sense, because differentiability guarantees continuity. Then, if you have a theorem that is if something, then something else, if differentiable, then continuous, you can turn that theorem around. We always call it the contrapositive. And the way the contrapositive works is take the conclusion and negate it. If your function is not continuous at A, well, go to your hypothesis here and negate it. That's your new conclusion. F cannot be differentiable. So that's really kind of our hint. This is not a numbered example, meaning the whole purpose of what we're about to sketch is just absorbing the theorem and its contrapositive. But if you use the contrapositive, you can sketch a function not differentiable by just breaking continuity. If you lost continuity, you've also lost differentiability all at the same time. So let's throw down some sketches and see just how we can break differentiability. We'll provide sketches of functions that are not differentiable at some specific point. So let's give this a try. As I go to draw this, let's put down first a curve that starts off nice. Then right here, I want to put in a discontinuity, but we have options, right? You could put all sorts of discontinuities. Let's start with maybe removable. That's what a removable discontinuity could look like. I could define a point above or below, or just leave it fully undefined. You've lost continuity in it either way. Let's say that's at a point A. Now, anyone have a volunteer for a next continuity, or excuse me, discontinuity we could sketch? At infinite discontinuity, that'd be a great one. Let's put it right across B. We'll say it's at this location. Put in a vertical asymptote. If our curve does this, we've also lost continuity right at B. Well, how about a third flavor of not having continuity? Anyone see a different way we can lose continuity? Absolutely. Let's put in a jump next. A jump means your curve goes to here, and then it just takes on some slightly different value or massively different value, depending on how large the jump, as we move across. So we'd have three discontinuities, and now we can say F is not continuous at x equals A, B, C, and so F is not differentiable at those values. So that's one way we can lose differentiability. Damage continuity, and then we have a big problem. Any questions about that so far, folks? Okay, so continuity is kind of a nice concept in a sense. It's something you can just see on a graph. It means when you sketch the curve, there's no holes in the graph like at A. You don't have to lift up your pen to jump across a vertical asymptote. And there's no jumps like, this one right here. Differentiability is even different. Differentiability says your graph is connected, no discontinuities, and also it's a smooth curve. So let's draw something that goes along those lines. Let's call this our first example, and I'll put just a quick border. And here's our next example of a function that's not differentiable. So it's going to start off just fine. Let's say it goes in that direction forever, then it comes around, and it does something like this. Functions can do that, but that's a really bizarre function. Imagine what it could mean if this was, say, a roller coaster, and x is, say, distance from the start, y is the height of that roller coaster. You would never want to ride this ride, right? Everyone's going to launch out of their seats on that kind of ride. It could be deadly. We'll call this right here corner, which is interchangeable with cusp. If you see a corner or a cusp, that is immediately a location where f is not differentiable. So we can say here, f is not differentiable at x equals a due to the cusp or corner. We'll consider that interchangeable. And you can almost imagine what the problem is. If we zoom in on this just a little bit more, the slopes become positive, positive, larger positive. The slope is becoming an extremely large positive number. Then right here, it transitions to suddenly terribly large positive numbers. Then right here, terribly large negative numbers. There's a huge jump in what happens to that graph. A differentiable function will never have that feature. Sometimes we just say briefly, differentiable functions give smooth curves. When you graph it, you're not going to cut yourself on the graph like you might on this one. And that might be a good thing to just add to the notes. Let's put here just as an aside. Let's say the graph of a differentiable function is, let's put this in quotes, it's not precisely defined, smooth. So that's the thing to look out for when you lose continuity, any kind of corner like what you see right here. Any questions with that second way of losing continuity? Okay, turns out there's a third way, and this is kind of bizarre. For my third way of breaking continuity, or excuse me, breaking differentiability, I'm going to put down a curve that is continuous. And it's going to go like this. But first, let me take these down again. Let's do this next example with that theorem in mind. If I can make that a little bit bigger, that would be great. Let me try. There we almost go. How about right there? Does that look readable to folks? Okay. So here's my next example. Let's let f of x be equal to x to the power of 1/3. It's a wonderful function, and in fact, it's continuous everywhere. Let's take a look at it on the graph just to get a feel for it, so we can zoom in on it as well. Not if it's a cube root. With a cube root, you can have positive and negative values for x as well. But if it was like, say, x to the power of 1/4, then yeah, we would have a problem with that. Say, here's a graph of x power 1/4. And we have undefined if we're going to the left on negative values. The odd roots will give us the entire real number line. Now, this does depend on the computer software you use. If you use Mathematica to do any kind of computations, Mathematica is too good with complex numbers for its own right. It actually doesn't plot this because it thinks you might be working outside of the real numbers in a larger space. So some software is a little bit weird on this. But for this curve, I mean, it's great. It's continuous. There's no holes anywhere. But there is one specific spot where we actually do lose differentiability. Anyone see where it is? It's 0, absolutely. There is one really bad problem at 0. If we put a tangent line on that, as we go through 0, anyone see what the slope of that tangent line would be? Exactly. So this is a vertical line, vertical tangent line, which means m, the slope, is undefined. I mean, horizontal tangent lines are great. Slope is always 0, but not for vertical tangent lines. And our second problem is, well, the derivative of a function at a number is the slope of the tangent line. And this is one scenario where a tangent line exists, but the slope has no meaning. We would say right here, f prime at 0 is undefined. Only because of it being vertical as a tangent line. if say we want to calculate the slope of that tangent line, we'd have to take on 2 points, right? Say this point is 0, 1, 2. Our second point right here would be 0, 0. But now if we try to calculate the slope of this line through the 2 points, it would go m equals, I'll use this as my y2, 2 minus 0. And then down below, we would get a 0 minus 0, which is undefined altogether. So really, that's our only weird issue. Again, it's strange. It's just a mathematical artifact in a certain sense that vertical lines have undefined slope. And if the derivative is equal to a slope at that point, the slope of the tangent line, this is one scenario where it's just undefined, even if the curve looks great. So here's the danger of theorem 4. That then right there is an arrow that only goes in one direction as far as the logic's concerned. Just because you have continuity, you cannot go backwards through that arrow and say you have differentiability. An if-then statement only runs one way. The contrapositive also only runs one way. The difference is you negate these values that are highlighted in the blue and the green. So even though we're continuous, no guaranteed on differentiability right at that point, making it just truly a bizarre value altogether. Well, any questions at all, folks, on looking at that last case here? Okay, this one is such a weird situation. I feel like it's worth taking a look at the homework just for this case. So let's take a look at assignment number 3. The problem I'm thinking about is stuff like, say, these things. Let's see here. So this is right out of our book, our next homework assignment. It says the graph of f is given. State with reasons the numbers at which f is not differentiable. Now, if we go left to right, that would be a number at -4 because of the corner. 0, it's not differentiable because of the jump discontinuity. But the author, I believe he intended this one to have a vertical tangent line right about here. So right around here is where it doesn't exist again. So that's hard to spot on a graph. It makes it almost not totally a fair question because there's a lot you have to interpret when you look at that thing. If it's on Desmos, it's more of a fair question because up here on Desmos, I can just zoom in on this long enough until I decide, yeah, that really would be a vertical tangent line. It appears vertical the farther and farther you zoom in onto that thing. So watch out for those kinds of situations. Vertical tangent lines, they're kind of hard to spot. I know, I agree with that. Other questions so far? Okay, well, this is kind of the graphical side of the note so far. We're going to get more into the computational portion where we're just going to crank out derivatives using the definition. But first, I have this wall of text that I typed out. The reason I typed all this out is we'll come back to some of this material. Like say, for example, all of this we'll come back to when we're in chapter 3. It's just worth taking a look at right now. But what's up at the top, this stuff, is definitely more important. It's more just notation matters. And one thing that gets really tricky in a calculus class is always the notation. I mean, even when you take a limit, there's a lot of machinery there on how you write that. X tends to A from the right or the left. Lots of symbols go into quantify all that kind of stuff. And same for differentiation. So we'll assume we're using function notation, y equals f of x, and some of these derivatives to indicate the independent variables x, dependent variables y. And when we write down a derivative, well, so far we've only been using that, f prime at x. These notations right here, f prime or y prime, is Newton's, as in Isaac Newton's, prime notation. Newton's prime notation is really nice. What's great about it is it's clean. Well, that's about it. It's really fast to write. It's very clean notation. It's not precise though. So even though we have a great way to write a derivative, Sometimes that's even better. Not always, but there's going to be cases where our formulas are stated in these weird ways, or sometimes we have word problems where the independent variable is not X, the dependent variable is not Y, and suddenly this notation becomes massively useful for us. So all this stuff, if you call it, let me try again, if you call it dy dx, or if you call it df dx, or if you call it d dx of f of x, this is Leibniz notation. So they're all saying the same exact thing. The qualities are just saying we are indicating a derivative one way or another. But this is what Leibniz notation is saying. dy over dx, that's not an actual mathematical fraction. That's just the limit as h goes to 0 in a different quotient. But it's saying you're taking the derivative of y with respect to the independent variable x. If you know, for example, you're taking calculus 2, calculus 3, these things get built upon. And so not looking at it in calculus 1 is a huge disservice if you're going further into calculus. Here we're just saying take the derivative of the function with respect to x. And this one's saying take the derivative with respect to x of the function. These are all used interchangeably. But for our purpose of our course, this section right here will be more common. And this section right here will be far less common. Our author mentions it because depending on the context you're working in calculus, you do still see these kinds of things. You might be working in vector calculus or something more nasty and they come up, but they're still just saying the same thing. F prime at x, you're taking the derivative. So those are the notations to become familiar with. We'll be practicing with these quite a lot, but we'll also be enforcing these just to get our eyes trained on what they're saying, how to work with them, and so on. Any questions about them at the moment? Okay, well, when it comes to Leibniz notation, again, it's not very compact. It's more precise because it's telling you exactly what's going on when you differentiate. And occasionally, if we have to evaluate a derivative, we'll write f prime at a for in prime notation. But in Leibniz notation, it's a very clunky thing to work with. It's something we'll see here and there. Here it's saying take dy dx, that's just going to be the derivative. This vertical bar is considered to be an evaluation bar. You can read this as the derivative of y with respect to x evaluated at x equals a. Or we could write out this way, f prime at a. So those are the differentiation operators. Any questions or comments at the moment? Okay. For this chapter, we're really going to focus on f primes or potentially y primes. In the coming chapters, we'll take a look more at the Leibniz notation as well. In fact, a lot of the author's formulas are just stated in Leibniz, so we kind of just become familiar with them as part of getting through the book. Now, we mentioned also, if you take the derivative of a function, that's also a brand new function. And so the purpose of this definition is to remind us that if f prime is also a function, f prime might be differentiable, and you could write it this way. The derivative of f differentiate again. That's extremely precise notation. There's nothing wrong with it, but just about everybody would write it this way, f double prime. F double prime means we differentiate something twice. Not going to do that a whole lot in this chapter, but again, chapter 3, we'll do quite a lot of that kind of stuff. So if you see a f double prime, that's your second derivative. Now, Leibniz notation always looks different. And this is what the second derivative is indicated in Leibniz. You take the derivative with respect to x of the derivative with respect to x. This portion right here is like the f prime and then the prime outside the parentheses. All that can be compacted into this. That statement is saying take the second derivative of the function y and differentiate with respect to the variable x both times. Now, again, the reason Leibniz is so important is if you have a multivariable function, you're probably in calculus 3, and this is going to come up. You could take the derivative of a function y with respect to x first, and then respect to something else, say z second. It'd be a second derivative, but now we're specifying the order and which variables to differentiate under. Not something we're doing in this class, but again, just a preview of why Leibniz notation is so precise. I can't give all this information with just one prime symbol. So that's my sell on definitely always try to stay familiar with Leibniz, even though we may not use it the majority of the time. When it's useful, it's invaluable. Other questions or comments so far, folks? Okay, then down below is even more text. I'm going to speed through this a little bit faster so we can focus on just taking more derivatives. But this is already familiar stuff. If we have a position function, s equals s of t, the velocity, v of t, is nothing but the derivative of position with respect to time. It's ds, derivative with respect to position, dt, the dependent variable is time. We can go even further to that. This is what a second derivative would look like. The second derivative of position is now your acceleration. We write it as v prime of t, or we could say it's s double prime of t. Or if we're feeling really fancy, we could write it this way. Acceleration is the derivative of velocity with respect to time, dv dt, or it's this, second derivative of position with respect to time both times. And it just keeps on going. The jerk function is the third derivative. It would look like this. I don't think we'll run into the jerk function, but it's interesting to mention now that we're talking about higher derivatives. Well, that's our walkthrough with notation. Last thing I want to take a look at is just more practice calculating derivatives. Essentially, exactly like we did in 2.7, the last part. But any questions or comments first, folks, before we try these out? Okay, well, we've got a good amount of time to give some nice examples on these. And my thought was, let's start off slow and build up towards harder and harder functions. So this is going to be our part A. It says, find the derivative of the function. I want to make the function f of x equals 2. Now, these are interesting problems if you have a constant function. If you have a constant function, it turns out you have the answer. Anyone happen to know it? It would be 2 exactly. Now, we didn't even use the definition of the derivative. We're thinking geometrically if you're thinking 2. And here's what that would look like. Let's graph the function. F of x is the function that takes on the value 2 for all x. So here it is. And now it doesn't matter where you are on this line, pick any value, the slope of the tangent line is still the horizontal line and its slope is 0, guaranteed. So this means f prime at x is automatically 0, just because it's a constant function. Now, we didn't actually solve the problem the way we're meant to. We'll use the definition of the derivative to get full credit if this was an exam problem. But if you have any inkling of what it should be, sketch a picture, throw it down, and now we have the answer before we start the problem. That's a good place to be in. Any questions before we now run through the definition of the derivative? Okay, well, the derivative is saying if we want to take f prime of x, then that will always be the limit as h goes to 0 of f at x plus h minus f of x all divided by h. I want to highlight that in yellow to just say that's what we mean by the definition of the derivative. We need to crank out that thing, but we've done it before, so this is just kind of a repeat of that routine. Its limit as h goes to 0. Now, having a constant function is definitely nice for us. If it says f of x plus h, you go here, but f always outputs 2. It doesn't matter what you're throwing inside here. F at x plus h is also 2. So we will take limit as h goes to 0 of 2 minus f of x. Well, you can think of that as a direct substitution. To depend on x, we always get 2 divided by h. This turns into the limit as h goes to 0 of 0. And why is that? It's because it's 0 over h. The whole thing becomes 0. The limit of a constant is that constant. And so if we follow the chain of equalities, yes, we have the derivative of f at x becomes 0. And that's what we were saying here when we gave it a first guess on what it should be. Well, any questions, folks, on getting through this one? Yeah. This one, say right here. Oh, this right here. Gotcha. So when we go to calculate, say, f at x plus h, what's really weird about that is we have to use this function, right? And our go-to method is you have to plug in your input to wherever x is. That seems like it's impossible this time, but it's actually possible. You could put in x power 0 if you really wanted to. That's bona fide because 1 is x to the power of 0. You're allowed to do that. So if you went with that strategy, you would say it's 2. X plus h goes in where the x is, which is raised to power 0. But because it's raised to power 0, this whole thing turns into a 1, 2 by 1, giving us just a 2. So if it's a constant function, even if it's f of x plus h, we still just get that 2 to come out. Does that make sense with that operation here? Gotcha. That's what's weird is, yeah, with function composition, you're expecting an x, but you could always throw it in. You can kind of cheat your way around it with a power 0 on your x. Other questions at the moment? Yeah.
So you stack 2 over h. Why is the 0 not like quantified? What is the 0 over 0?
Only if we did use direct substitution. The one step that I kind of skipped over related to that question was, we went to that next step, we get limit as h goes to 0 of 0 over h. Now, I wouldn't want to use direct substitution here because, like you said, it's 0 over 0, undefined. So what we do next is we just simplify. And what that would simplify to is just 0 immediately. So our h does cancel in this one way because it goes into h 0 times, turning into this right here. Does that make sense? Think of it that way?
Yeah.
Gotcha. There becomes a limit of the constant, and we just get a 0 to come out. Other questions with this one so far? Yeah, go ahead.
So when you're like finding, would this be kind of like finding f of a?
It would be, yes. The only difference is we're using x instead of a.
So when you would find a number, would that be what you chose?
No, it would be where the x goes. Yeah. H is just a quantity that's getting smaller and smaller. I think the best picture for that would be, let's take a look at 2.7. This right here. So they gave us the definition of the derivative really right here. We just called it the slope of the tangent line because we were building up to it. What we did is we built this line right here in the light green, the secant line. We start with the base point, a f of a, and then just to get a slope, we have to have a second point. So h is just a tiny increment away from a. Essentially, yeah, it's a placeholder that's shrinking. Right, yeah. So think of h as just a placeholder, an increment. The reason the limit is going to 0 on it is because we want that point to overlap so that we can get that true slope out. But does that make sense with the h value there? Gotcha. Other questions so far? Okay, well, we did the definition of the derivative. This one was kind of an easier one. How about a really hard one? Does that sound all right to folks? All right, let's try something that is just not the funnest problem, but it's something if you're really careful on your algebra, it is obtainable. Here's part B, and I have a actual problem that I wrote down for this one. Let me have my notes. Part B is going to be f of x, uppercase f of x. It's a fancier function, I guess you could say. It's defined to be x squared minus 1 divided by x plus 3. And hopefully I get through this one while my voice holds out. This one is kind of like the question that started us out today, doing the definition of a derivative with a fraction. Also, I think there's another problem like this in the homework as well, where we're going to have to walk through the definition and we're have a fraction to deal with. So let's do this one carefully. I think I'll need a new page. Let me just, oh no, let me try to make that happen. Microsoft is actually not friendly when it comes to this kind of stuff. It just sort of does what it wants. But we'll make it happen. Let's go down here. Okay, there's our part B. This won't even go away, will it? So first thing we want to do is we're meant to calculate this using the definition of the derivative. So we'll write f prime at x equals the limit as h goes to 0. I'm going to use color coding on this one because we want to be very methodical. In the difference quotient, it's f of x plus h minus f of x all divided by h. So that's our challenge to get through so far. We have dealt with fractions before, but this one involves x in two different locations, one of which is squared. And so that's what the extra difficulty is on this. The algebra is just a little bit more gnarly than normal, but still the familiar algebra we've seen all along. We'll go limit h goes to 0. First thing I want to do is make this more readable by factoring out h, like we typically do with fractions. It's totally optional. So if you don't like it doing that, I'd say skip it. If it looks more readable to you if you take this step, then it would have some value. Now, next thing, I'm going to put in f at x plus h using blue. That means I'm throwing x plus h here, and it comes in as x plus h squared minus 1 divided by x plus h plus 3. So those are my two substitutions from this original function here. Does that look right to folks on the function substitution? Pretty much what I did was I took this x, which goes to x, but instead put in x plus h in that kind of way. Or if we visualize it this way, if we rewrite f of x, but use placeholders, here's what it looks like. What I mean by placeholders is, this is the same function. Function of something becomes something squared minus 1 divided by something plus 3. But you can put anything in there. Functions are extremely malleable. You could put another function. In fact, x plus h is another function. And it would look like this. X plus h, x plus h, x plus h finally. So I kind of the strategy that helps a lot is just put something blank for x, rewriting the whole function. Then f of x plus h, just fill it all in and you have the right thing. Does that make sense, visualizing it that way? Awesome. I'd say that's the trickiest part on starting off because we're really doing a function composition. But then it goes minus f of x in green. That's just the original function, no change. So x squared minus 1 divided by x plus 3. So now we have a limit. It is a fraction and it still has issues. Sorry, question? X minus 3. Are you looking at the blue or the green? Oh, over here. So x squared minus 1, x plus 3. Well, the x's here wouldn't cancel. What was your question about the x's or the h's? Sorry. Oh, the h's wouldn't cancel so far at this stage. If we try to say cancel this h, it would later, but we'd have to divide it through everything in all of these numerators. So our goal is to get to a point where the numerator only involves h, so we can cancel that h there. Right. Other questions about that so far? Did that answer your question about the setup so far right here? Gotcha. Other questions at the moment? Okay, once we get to this stage, here's what I would do as a next step. I need to expand this out because it's going to be an eventual next step. So we'll write this as limit h goes to 0, 1 over h with a bracket. Now I'll keep this in blue and write x plus h to the power of 2 becomes x squared plus 2xh plus h squared. And that's just foiling out x plus h squared. Now I'll type in -1. We want a really long fraction bar of this step. And I'm just copying in the denominator, x plus h plus 3. Then minus, and in green, I'm just going to make it a long fraction bar, but nothing special happening to it. It's still just x squared minus 1 over x plus 3. Now, once you're at this spot right here, let me just for a moment zoom to the top. We're doing the same thing as we did right here. It's just that the algebra is a little bit more than this one. But we're going to line up our denominators, add the fractions together. And then once we start canceling, that h right here, which has to go away so we can take the limit, it will cancel, provided we make no missteps. So here's what the next steps are going to look like. I want a parentheses around every numerator and denominator with what we have so far. Next, we need to construct the least common denominator. So we just look to the denominators and insert what's missing. And you'll see where we should insert right here by the red dot. Exactly, or it should be an x plus 3 from, yeah. So x plus 3 goes below and above. Then on the second fraction, same idea. The thing that's missing is x plus h plus 3. So drop it below and above as well, x plus h plus 3. And now we're in business, folks. It's just that it looks really, really bad. We have lots of terms to take into account. And so this is one of those problems where if you go slow, that's the strategy, because we have to account for every single term and cancel it just right. So here's our next slow and methodical steps. Limit as h goes to 0, 1 over h is going to multiply one overall fraction since we're adding them together. The common denominator is x plus h plus 3 times x plus 3. And now in the numerators, there'll be this numerator here minus this numerator over here. Now, I guess we have some steps we could take on this. We could expand this right now, expand this one, and then distribute the negative sign in. So I guess let's try it going that way. If we FOIL out all of this stuff, here's how I'm going to visualize it. I'm going to take this x and just do a distributive plot. So it's going to become x cubed, 2x squared h, plus 2x squared h, plus plus 8x h squared, then finally minus x. So that finishes off the first distributions. And please let me know if I forget anything or mess up an exponent. That's all it takes to ruin the problem and get stuck. Next, I'll distribute the 3 through. So if you like arrows, it'll be 3x squared plus 6xh plus 3h squared minus 3. So that finally takes care of the full expansion of those two polynomials. Then we go over here and we do it all over again. We have to be extra careful with the negative sign. So I'll start with a negative and a parenthesis, and I'll just hope that it all fits in there. So I'm running out of space. Easy to paint yourself into a corner with these kind of problems. And if you turn your paper sideways, then that's a decent strategy sometimes to do these kind of limits. Well, any questions, folks, so far? Okay, same idea. This time I'm going to distribute in x squared in this way. So we'll have x cubed plus x squared h. And then here to here plus 3x squared. Finally, the last distribution. And it kind of gets easier as we go. If we're distributing -1, we're just negating everything. So that's minus x minus h minus 3. So that's all our terms in a row. Does it look okay to folks so far? Awesome. If we did this fancy, you could have distributed your negative all at the same time. And if you're curious what that would look like on paper, I'm going to erase this in a moment, but this is a decent shortcut just to save on writing. You can force that positive, distribute the negative sign in that way, and just distribute a negative x squared and a positive one. That takes care of that negative sign all at once. If you did it this way and just left it a negative sign, we'll distribute later, you're being a little bit more careful, so no harm done. So we're off to the next step. All I'm doing in the next step is distributing that negative sign. So I'm going to drop the color coding at this stage and carefully write it out. And this is one of the stages where I tend to make a lot of mistakes, because when I copy from one line to the next and I'm in a hurry, I might drop x h squared. Now the whole problem is off. So again, go slowly, methodically, maybe even count the number of turns. And we should get it all in exactly as it should go. This time it's just one fraction bar, because I'm going to multiply the denominators across h, x plus h plus 3, x plus 3. I notice we're not expanding the denominator. It's actually simpler in this factored form, especially since our goal is to cancel that h, not distribute it in, kind of hiding it. Then up above, I'll methodically copy these in. It goes x cubed, 2 x squared h, plus x h squared, minus x, plus 3x squared, plus 6xh, plus 3h squared, minus 3. Here's where we negate everything. Distribute in the negative sign, and we'll get minus x cubed, minus x squared h, minus 3x squared, plus x, plus h, plus 3. So now we've got it all in there. And this is the hope and the promise. If all of our algebra was done completely correct, that h right here must be eliminated. And the only way you can cancel this h algebraically is if every term, like x cubed, that doesn't have a factor of h tacked in, it has to cancel. So there's got to be opposite, and here it is, way off to the right. 2x squared h. Let's see if it cancels. I don't see anything, but what I do see is that this has a like term, negative x squared h. So they don't cancel, they combine. X h squared, I don't see anything, but that's okay. It has h, it doesn't have to cancel. This one at negative x does go away. There's a positive x to go with it. 3x squared has a negative 3x squared to the right. And what about this? 6xh? I don't see anything. I mean, it doesn't combine with this because the power of h is squared on that one. And it's power 1 here. 3h squared, I don't see anything. But minus 3 and positive 3 have to eliminate. That's all of our cancellations. So let me now write out limit as h goes to 0. And let's see, what do we have for our survivors? I circled this one because it combines with that one. So 2x squared h minus x squared h gives us x squared h plus x h squared. Skip a couple, plus 6xh. Then I think that's the last one, plus 3h squared. All of which is still divided by h times x plus h plus 3 times x plus 3. Plus, thanks for spotting that. See, that's the one way I definitely would make a mistake on this one. Plus h, good eye. So plus h, slightly longer fraction bar. I think we're in business. Does that look all right to folks so far? Okay, note every term does involve h, so you can cancel it. There's a couple ways to cancel it. If you like the factoring method, it's a little bit more writing, but at least it's precise. It's limit. H goes to 0. In the numerator, I'm just factoring out h. It'll leave at x squared plus xh plus 6x plus 3h plus 1. Visualize distributing h back and see if you get the right powers. We would get x squared h, xh squared, 6xh, 3x squared plus h. I think we've got it. Down below is h, x plus h plus 3 x plus 3. And this was the one cancellation that we're essentially gunning for every time you do this problem. That h has to go away. And here's where it happens finally. It cancels with that one h we factored out. But after you do that cancellation, the limit as h goes to 0, like folks are mentioning, you can do this limit now. Anything that still involves h converges to 0 in that limit. So that term is gone. Over here, it would go to 0. We're using essentially just direct substitution. We have a continuous function in the variable h. And down below, the last h here, exactly, only because of that 0 here.
Then it was the one that all of that idea was.
Exactly, absolutely. In fact, we would have been able to put one in right at the very start because we wouldn't have been dividing by 0. We would have just been done immediately.
That's why I said that.
Well, other questions so far, folks, to that stage? Okay, all you have to do now is just write the result. Because we use direct substitution, sending h to 0, we don't write the limit statement anymore. We just write the survivors. X squared plus 6x plus 1. Down below, it's x plus 3 times x plus 3. So the most compact way to write that is x plus 3 squared. So now we have it, folks. That is, let me double check. Yeah, I got the answer there. I'd like to have the answer for this one. It's a lot of writing. That's finally our actual derivative. What they'll tell us is, pick a number, any number in the domain, plug it in down here. That will be the slope of the tangent line to the graph of that nasty function right at that point. So that's the promise with all this machinery. Any questions at all, folks, on getting through this kind of problem here? Okay, well, sorry, we went right to the minute on this one. I definitely want to do one like this since there are fractions in the homework. I don't think any are quite as bad as this, but they do get a little bit hairy, like the one we started in class today. Well, have a great night, folks. If you have any questions, I'll be happy to help out. Next. Oh, sorry, thanks for reminding me. And I do have your homework. Annie Miller? Gabby M. Please let me know if I mispronounce your names. I can accidentally do it the whole semester if you don't stop me. Rena? Rihanna? Raina, gotcha. We'll get it there. So. Any slide? See there. Anyone? Yeah, awesome. Well, we're gonna drop this in the first as well, so. Sorry, to hear that. So. Chapter 2. Yeah. Second out. Yeah, I'm still
number of considerations compliant.
Three is just going to be.
Gotcha. I'll be happy back, and I'll come back to you. Gotcha.
What's the name?
Matthew Paul.
Matthew Paul.
Oh, did you join the late?
Yes.
I don't think I've gotten yours just yet, but it's, what I'm passing back right now is this assignment one right here. And since you're joining the class a little bit later, I can accept that one with an extension. If you click on the assignment one, it brings up the exercises as well as the solutions in the back of the book as PDFs. Sorry, say again? Sorry.
I'm sorry. When would you need to turn it in?
I would say if you could get it in by